Okay guys, Swastyak here, and today we're going to be doing AP Physics B 2005 question 2. A simple pendulum consists of a bob of mass 1.8 kilograms and is attached to a string of length 2.3 meters. The pendulum is held at an angle of 30 degrees from the vertical by a light horizontal string attached to the wall as shown above. So question A is asking us to draw a free body diagram, which is something that you should do in these type of questions at all times. So the first force is going to be the force of gravity, which is always present, and it's going to be pulling the object down. So this is going to be Fg, which is equal to mg. Next, we got the force of the light horizontal string attached to the wall, which is going to be this way, and this is going to be F of tension 1, which is going to be equal to force of the tension of the horizontal. Or in other words, okay, and now we got the tension of the string that's keeping this object in a pendulum type form. So this is going to be force of tension 2, which is going to be equal to tension of the pendulum. And this is going to be a 30-degree angle. Okay, so for part 2, it's asking us to calculate the tension of the horizontal string. Now we know that this object is in equilibrium because it doesn't say that it's moving anywhere, and this horizontal string is preventing this from being in a pendulum motion. So we know that since this object is in equilibrium, the force net is equal to 0. So that means that we can split this up into components and get F net of x direction is equal to 0, and F net of y direction is equal to 0 as well. So going back to this as well, we see that there's the component here that's not in either direction because it's at an angle of 30 degrees. So we can make this force of tension 2, otherwise the tension of the pendulum, into two components. So right now, you can see that we have this 30-degree angle, and we can make this T pendulum sine 30 and T pendulum cosine 30. So the cosine angle is going to be what's in the vertical direction, and T of pendulum in sine 30 is going to be in the horizontal direction. So using this, we can find the F net of x equal to 0 and F net of y equal to 0 using the Newton's properties to help us solve this question. So we know a bit more about F net of y because there's mg and there's force of tension of the there's force tension of the pendulum in the cosine direction. So we're going to know that tension of pendulum cosine 30 minus mg is equal to 0. In other words, tension of pendulum cosine 30 is equal to mg. So we can set this up to be tension of pendulum is equal to mg over cosine 30 degrees. So now we can go to the x force, which has a bit less of information. So we know tension of the horizontal string minus the tension of the pendulum string in the sine 30-degree component is equal to 0. So we know tension of a horizontal string is equal to tension of pendulum sine 30. But here we already solved for tension of pendulum, so we can use this and plug this value here. So tension of the horizontal string is equal to mg sine 30 degrees over cosine 30 degrees. And we know that sine over cosine is equal to tangent. So we know that the tension of the horizontal string is equal to mg tan 30 degrees. And now we just need to plug in the values. So we know that m was given to us as 1.8 kilograms, and g is equal to 9.8 meters per second. So we have 1.8 kilograms times 9.8 meters per second, meters per second squared, times tan 30 degrees, which is going to be equal to 1.8 times 9.8 times tan 30 is equal to 10.184, which is approximately 10 using significant figures. So we got 10 newtons for the horizontal string. Okay, next. The horizontal string is now close to the bob and the pendulum swings downward. Calculate the speed of the bob at its lowest position. So basically what's happening now is, in this system over here, the string has been cut and it's asking us to find the speed when it reaches here. So this is point A, the initial position, and this point here is point B, the final position. So we can use properties and know that that energy in a system is conserved in a perfect world. So using this, we know that EA is equal to EB due to conservation of energy law. Now we also know that at the highest point, which is EA in this point, is going to be the gravitational potential energy max. And lowest point is going to be kinetic energy at its max point. So we know that mgh is equal to gravitational potential energy is equal to kinetic energy. This is only going to be in the max and the max because the min of each of these points are equal to 0. At its lowest point, gravitational potential energy is 0, and at the lowest point, kinetic energy is max. However, vice versa, the highest point, kinetic energy is 0, and gravitational potential energy is at its max. So here, there is no gravitational potential energy at point B, and there's no kinetic energy at point A. So we get this simplified version of mgh at point A is equal to kinetic energy at point B. And now we can solve for this. So we know mgh is mgh, and kinetic energy is 1/2 mv squared. And we can cancel out the masses since that does not change in this equation. So we're going to have 1/2 v squared is equal to gh. In other words, v squared is equal to 2gh. And v is equal to root 2gh. However, what is h? So h is not just going to be the length of this string. Rather, it's going to be the difference. It's going to be this height here. Delta h is going to be what we actually need. So this height here is going to be L, say. And with this 30 degrees, we know that this is going to be L cosine 30 degrees. So using this, we can plug everything in. So v is equal to 2 times 9.8 times square root of, times parentheses L minus L cosine 30. And doing this will get you square root 2 times 9.8 times 2.3 minus 2.3 cosine 30, which is equal to 2.45, which with significant figures is 2.5 meters per second.